want to do to start today is give you an example of one of the questions that is going to be on the next test. So in the written response section, you already know what one question is. That last page of the worksheet, right? It'll be about that. The second question will be related to formula determination. So I thought, because as I often ask you to try to do, imagine you're writing a test, and then you're at home and then check your answer to see if it's right. I thought it would be appropriate to give you a test question. So I searched my plethora of files, and I went back to 2019, when you guys were in, what, grade 5?
About, yeah.
So this was question number 2 on that test, back when you were in grade 5. There's A. Caffeine is a stimulant. Let me just enlarge it a bit. My touchscreen sometimes works, sometimes doesn't. So this is out of 5 marks. Gary asked you about caffeine in one of the review questions, although he just stops at the empirical formula. Caffeine, the stimulant found in coffee, tea, and chocolate, is analyzed and found to contain 49.48% carbon, 5.15% hydrogen, 28.87% nitrogen, and 16.48% oxygen by mass. Determine the empirical formula. And remember the steps. Mass amount of each element are given or determined. Michaela, it would be easier for you to move closer to the middle. So that means in 100 grams, those are the grams of each element. Converted to moles, smallest whole number ratio. And remember one of the examples Gary gave us, you ended up with a 0.5 or a 1.5 or a 2.5. That means you got to multiply through by 2. That's part A. Part B, which I'll put in a second, says here's the actual molar mass, what's the molecular. So, not to ruin your morning, but pretend you were writing a test. That was the test back when you were in grade 5. Mr. Mesa. Remember, don't round it. I've given you 4 sig figs, maybe carry 5 through in the steps, and the more sig figs you carry through, the closer it'll get to the, sort of the whole numbers you're looking for. If anyone's finished, just suggest what it is you got. Second step is to convert the mass amounts to mole amounts. So 49.48 grams of carbon, convert that to moles. Do the same for hydrogen, nitrogen, and oxygen. Divide by the smallest of those values, which will be the moles of oxygen. And that should give you, I think in one of those you're going to end up with a 2.5, which means you're going to have to multiply through by 2. Finished? The empirical formula? What do you get?
C4H5N2O.
C4H5N2O. So when you divide everything by the moles of oxygen, then you get 2.5, 2 and 1. You're gonna multiply through by 2 to turn it into 5. Or maybe you get 5 directly. But the point is, that's just the empirical formula. I put it on because we didn't do any that had 4 elements in it. I think the only ones we did are 2 or 3. But I want everybody to get that first, and then I'll give you the molar mass, because that's not the molecular formula. Part B, which is how I'll do it on the test. I'll give you an A and B. Part B is, if the compound has a molar mass of 194 grams per mole, determine the molecular formula. How do you do that? Well, that's the empirical formula. The empirical molar mass of that, divided into this, has to give you a whole number. So if we were just going to go to 1 decimal place, 4 times 12, 48, and 5. 48 and 5 is 53. 53 plus 28 is what? 81. 81 plus 16 is 97. So the empirical molar mass is 97 grams per mole. Divide 194 by 97, you get 2. Which is a way of finding out if you did it correct. So the actual molecular formula is C8H10N4O2. Which, by the way, tells you virtually nothing about how the atoms are connected together. That question's out of 7 marks. A lot of what you did on the worksheet is what that is, converting mass to moles. Now, I wouldn't need to see, when you're calculating the empirical molar mass, in 1 mole of C4H5N2O, this many grams, this. Just write, once you get that, write empirical molar mass equals. And then you would just have to say 97 point whatever grams per mole. You'd have to show me then how you got this. You'd have to divide that by the empirical molar mass you calculated. And when you get that multiplier, don't leave it like this. Right, therefore molecular formula is this, okay? Now, Gary asks you about caffeine on, I think, review question, let's see, number 7 on page 145. But he just gives you a sample of caffeine is analyzed, he gives you the mass values directly. And he doesn't ask for, okay, turn the empirical into the molecular. And I think he's put a QR code there because there's actually 4 elements, and I don't think any up till there has required 4 elements. But all he asks is for the empirical formula. But on a test, the test you guys write at the end of chapter 3, the question on formula determination that I'll give you will have 2 parts. It'll be a molecular compound for which you first calculate the empirical formula, and then given the molar mass, calculate the molecular formula. And in this case, let's say the actual molar mass was 97 grams per mole. Well, then you're done. That is the formula. But if it's not that, it has to be a whole number multiple of that. So if when you get your empirical formula and you work out the empirical molar mass, if you then divided it into 194 and you got 2.38, well, probably the empirical formula you have is incorrect. Okay? Now, in terms of the remaining review questions, I wouldn't worry about number 8. I'm not actually sure what Gary means when he says atomic percentages. I'm not really sure what he's after. Maybe in every 100 atoms, that many are aluminum, that many are silicon. I don't know. I don't really understand what he's talking about there. And I wouldn't worry about number 12. But the other ones are pretty straightforward. And as a matter of fact, I don't think any of them would be as complicated or maybe as time-consuming as this question. Okay? So if you can do this one, you're probably pretty good with formula determination. What I want to do now is, if there aren't any burning issues associated with 3.5, let's go with 3.6, which is the last section. Up till now, if we harken back to the wheel model that chapter began with, seems like a long time ago. Notice that all of our mole conversion factors had 1 in front of moles. So, for example, number was 6.02 times 10 to the 23 items per mole. Molar mass, a certain number of grams per mole of the substance. Molar volume, a certain number of liters per mole. But all of those were referencing pure substances. The 4th addition on that rim of that wheel also had a volume, but it was volume of a solution. And in that conversion factor, the 1 isn't in front of the moles, the 1 is in front of liters. So rather than something per mole, it's moles per something, right? Many chemicals are dispensed in solution, and most chemical reactions occur in solution. And in the solution, the reaction is usually not the solvent. So for example, the reaction's happening now in your body, that solution is an aqueous one. But what's reacting is not the solvent, it's the things dissolved in the solvent, the solute, okay? Either molecules or ions. Recall that a solution is a type of mixture in which the chemical species are completely mixed. A solute is a minor component of the mixture, generally what has been dissolved in the solvent, the major component of the mixture. The vast majority of solutions you guys are going to see in chemistry are aqueous ones, where the solvent is water. Concentration is any expression of the proportion of a chemical in a solution. And the chemical in the solution is what's actually reacting. That's what we care about. Chemists need to know the amount of solute present in any volume of solution they might dispense. Another way of saying it is, if this is what's reacting, and the only way they can add that in a reaction to something else is in the solution, well, the volume of the solution has to have a way of telling them the amount of solute that they're getting, okay? Therefore, concentration is most usefully expressed as an amount of solute per volume of solution, rather than amount of solute per volume of solvent. Because we're not dispensing the solvent, we're dispensing the solution with the solute in it. Now, what's our SI unit for amount? What's the title of this chapter, you guys?
Moles.
The moles. So does it make sense that if concentration is most usefully expressed as an amount of solute per volume of the solution, that perhaps moles of solute per liter of solution might be useful? That's the most common way for chemists to express concentration. Now, there's other ways. Common units of concentration express the amount of solute in grams. These include grams per liter of solution, percent mass by volume, which is the number of grams per 100 milliliters of solution. Parts per million are also used. But the most common is this: moles of solute per liter of solution. So, and we refer to moles per liter as molarity. And we abbreviate it with a capital M. So for example, if I had a solution of hydrochloric acid, and I saw on the reagent bottle 1.8 capital MHCl, this is the solute. And this tells us in every liter of that solution, I got 1.8 moles of this. So that M doesn't stand for moles, it stands for moles per liter of solution, not solvent. Molar concentrations allow chemists to directly compare the number of particles in the same volume of different solutions. For example, if I have 10 milliliters of 2 molar, if a solution contains 10 milliliters of 2 molar lithium ions, that contains twice as many ions as 10 milliliters of 1 molar sodium. Now, I don't know if I like that example because that suggests I can make a solution with only lithium ions in it. I can't go to a shelf and get ions. I gotta get a compound that has lithium in it that would dissolve in water, or a compound that has sodium in it that would dissolve in water. And he'll actually bring in ion concentrations near the end of the section. If molar concentration is moles of solute per liter of solution, that means if I'm given any volume of solution, I should be able to get moles of solute. Given any number of moles of solute, I should be able to calculate the volume of solution that contains them. So for example, let's say I had 3 molar HCN. What is the name of that acid?
Hydrocyanic.
What's CN minus called? What's that ion called? Cyanide. And if the anion ends in ide, it's a hydroic acid. Vast majority of the time that's a binary acid, but here we have a polyatomic ion that ends in I. Hydroxide is another example. But hydrogen cyanide is a gas, but in water we call it hydrocyanic acid. That capital M means in every liter of this solution, I've got 3 moles of HCN. Those two are equivalent. In this solution, 1 liter of that equals 3 moles of this, which gives me 2 conversion factors. If I wanted to convert volume to moles, I would use this conversion factor. Liters would cancel. If I wanted to convert moles to volume of solution, I'd use this one, where moles would cancel and I'd get volume. All we've done here is to that wheel add 1 more spoke and 1 more point on the rim. But the conversion factor does not have 1 in front of moles. Could it? Could we have a 1 molar solution, 1 mole per liter? Sure. But the 1 doesn't have to be in front of the moles. It has to be in front of the liters. Here he gives us 2 real straightforward examples. One converting from volume to moles, another one converting moles to volume. The average salinity of seawater is 0.6 molar. How many moles of salt are in a toy bucket containing 435 mils of seawater? If you want to use the wheel model, which I don't know if it's even necessary at this point, but moles goes in the middle. We have liters of solution there. Now he's given us in milliliters, but that's 0.35 liters. If you want to know how many moles, we simply go through concentration. We want liters to cancel, we want to end up with moles. So, moles per liter. 0.35 liter, 435 liters. And don't write this, don't write 0.60 capital M per liter. The M means moles per liter. So capital M over liters makes no sense. So liters cancels, we end up with moles. Now he says there's no conventional abbreviation for solution, but SOLN, I usually put a period after it, but I guess some people don't. But that's just an abbreviation, all right? And the other thing we could do is we could start with moles. What volume of 3 molar hydrochloric acid should a chemist use to obtain 0.25 moles? Well, now we're starting here. We have moles of HCl here, and we want to know volume of solution. If we want moles to cancel and end up with liters, then that must mean that moles is on the bottom, liters is on the top. But notice, it's not 3 liters per mole, it's 3 moles per liter. That's why you would let the units guide you. Moles cancel, 0.083 liters or 83 milliliters is and again, if we can go to moles or come from moles, we could also add masses here. What volume of a 3 molar solution would contain a certain number of grams of HCl? Or this volume of this solution, how many grams of solute will it contain? That type of thing. And we're going to try to go through as many of those different conversions as we can. For the first time in the book, when you turn the page, you see an insert that I've added. This is another way to look at molarity. I'm not suggesting that it's necessarily a better way. At some level, I don't care what method you consider to do the calculations, as long as the work is shown properly and the answer is right. I don't care. The reason I'm introducing this here is mostly because what I'd like to add, or at least introduce to this section, is a topic of dilution, which is often quite a common question in solution chemistry. But the wheel models don't work for dilution chemistry. That's why I've added this here, okay? We know that molarity is a measure of solution concentration expressed as a ratio of moles of solute per liter of solution. For example, an aqueous solution of sodium chloride in which 2 moles of NaCl exist in each liter of solution would be labeled as 2 molar NaCl. We rarely add that because the assumption is, unless we're told something different, the solvent is water. So you would just see 2 molar NaCl. The M is a chemist's shorthand representing moles of solute per liter of solution. Because the solution is a homogeneous mixture, regardless of the volume of this solution we measure out. the concentration will always be the same, 2 molar. Remember we said back, I think during the first week of school, the reason we graph is to find a mathematical relationship between 2 measured quantities. So if we wanted for this particular solution to find the mathematical relationship between the moles of solute and the liters of solution, we just draw a straight line graph that goes through the origin. The slope of the line would be molarity. That's the y variable, that's the x variable. One useful way we can think of molarity is to imagine a graph where the y variable represents the moles of solute, the x variable represents volume of solution measured in liters. Using the above solution as an example, we could measure out several volumes and in each determine the moles of NaCl present. By plotting all of those points, those ordered pairs of x and y, we would obtain a straight line graph with a slope of 2. Obviously, if you've got no solution, you've got no moles of solute. The units of that slope, the m variable, are moles of solute, whatever it is, per liters of solution. Now, you might ask how in any particular volume, would we determine moles of solute? Well, carefully measure out a volume of that solution, evaporate it to dryness. So start with any volume you want. In the case of an ionic solute, evaporate all the water off. You're going to be left with a mass of sodium chloride. Convert that to moles. And when you plot all of those pairs of data, it has to go through the origin and it has to be a straight line. It's straight because it's a homogeneous mixture. Regardless of the volume you pick, the concentration is the same. Okay? This proves to be a useful way to view molarity because the majority of these problems requiring calculations involve solving for moles of solute present, the y variable, from which we can also determine mass, volume of solution, the x variable, or concentration of the solution, the slope. The wheel model works fine for the first two, moles or mass of solute per volume of solution, or vice versa. But calculating the slope of the line, the molarity, isn't something that the wheel model helps you with that much. This normally will be given 2 or enough information to calculate 2, and it's effectively deciding which of the 2 values were given and using them to solve for the third. And again, it's not imperative that you consider this way to look at it, but when we do dilution chem, you'll see why it helps a bit. So here's an example. What volume of a 3 molar solution sodium nitrate will contain 0.45 moles of solute? That was an example Gary just did, okay? We can view this question as asking us to determine the point on the x-axis, volume, which corresponds to a y value, moles of sodium nitrate, for a graph with a slope of 3. So, we know the slope of the graph, which is the molarity. 3 capital M means 3 moles of sodium nitrate per liter of solution. And you don't really have to write this down, it's right in the book, okay? We usually begin the calculation with the given value that represents the actual quantity. So we're turning one quantity, moles, into another quantity, volume. And the glue that gets us there is the slope of the line. So on the y-axis, where we have moles of sodium nitrate, we start at 0.45. We know the slope of the line. All we're doing is calculating volume, liters of solution, okay? And y divided by m equals x is the y variable. There's 1 over the slope, not 3 liters per mole, but 3 moles per liter. Moles cancels, there's the volume of the solution, all right? Now, we could have also said, instead of moles of sodium nitrate, what volume of a 3 molar solution of sodium nitrate will contain a certain number of grams? Well, then we'd first have to go to moles before we went to the volume, all right? Now, number 2 is a bit of a step up. Let's reword number 2 just a second. If the question asked, how many moles of calcium chloride, or let's go back to this one. How many moles of sodium nitrate would be in a particular volume? We could do that, right? We could also be asked, if we've got that slope and that volume, what mass of the solute? Because if we can get moles, we can get grams. That's kind of what example 2 is. Describe how you would prepare 2.5 liters of a 3 molar solution of calcium chloride. Any solution whose concentration we know that we intend to prepare, we call that a standard solution. And if you look on page 150, here he tells us, bottom half of the page, a solution of known concentration is called a standard solution. When we make a standard solution, we begin by finding out the amount of solute we need, and then we write the recipe for the solution once we have that, okay? If the solution we're making begins with a pure solute, that involves calculating the mass of the solute we need. So, describe how you would prepare 2.5 liters of a 0.3 molar aqueous solution of calcium chloride. Well, because the solute is calcium chloride, that goes here. There's the liters of the solution. The concentration we want is 0.3 moles of calcium chloride. Okay. So we know the volume we want to end up with. We know the X variable. We know the concentration. So step 1 is to get moles of the solute we need. But you can't measure moles on a scale. No scale measures moles. So whereas that would be step 1, step 2 would have to be to calculate the mass we need. So we're given the volume and molarity. This allows us to calculate moles, the Y variable. And again, Y is just equals mx. So the slope times the volume, which can then be converted to grams, because this is the only thing we can measure. And that's exactly the example that Gary gives us, preparing a standard solution from a solvent, all right? So the arithmetic that we have to calculate, there's step 1, to get moles of solute, liters cancels. Step 2 is to convert it to grams. Now, if we had started with 2.5 liters of a 0.3 molar solution of calcium chloride and evaporated it to dryness, we would find that mass sitting in the bottom of the container. But we're asked for the recipe to make the solution. So this isn't a recipe, that's just the mass of the solute we're going to need. So now we have to write how we would make this solution. Some students would say put 83.3 grams in a container, add 2.5 liters of water. But remember, it's not moles of solute per liter of solvent, it's moles of solute per liter of solution. The recipe for this solution therefore reads, place 83.3 grams of calcium chloride in a graduated container and add water to a final volume of 2.5 liters. Don't add 2.5 liters of water, because if you add that to 83 grams, you're gonna end up with more than 2.5 liters of solution. Whenever we make a standard solution, the graduated containers that we use are called volumetric flasks, and that's what we have here on your right. They come in various sizes, but they all have a similar shape. They all got a big bulb at the bottom and a narrow neck. And at some point up that narrow neck, there's a little line. You guys see that little white line? The narrow neck allows for a precise measurement of volume. So this is a 250 milliliter volumetric flask. This is a 500 milliliter, this is a 1 liter. They come in all sizes. But they're only intended for one thing, to make a standard solution. So we add the solute to the bottom, then we add water till the bottom of the meniscus is on that line, usually about halfway up the neck. And then each of the flasks, or the volumetric flask, comes with stoppers or caps that go on the top. And because we want the mixture to be homogeneous, then we usually invert it several times. All right? So that's the only thing these things are used for, to make a standard solution. If you take Chem 12 next year, if I'm still here teaching it, we'll talk a lot more about volumetric flasks in a technique called, an analytical technique called titrations. So here's the recipe. Place 83.3 grams of the pure solid in a graduated container and add water to a final volume of. Don't add 2.5 liters of water, because that'll be incorrect. Now, we calculated moles from volume. We calculated volume from moles. But what we haven't done yet is calculate the slope of the line. Gary does that for you on the top of page 151, but notice he doesn't throw out a little wheel there, because the wheel doesn't lend itself to concentration calculations. The graph kind of does, but not the wheel. What is the molar concentration of a solution that results when 150 or 15 grams of sodium chloride is dissolved in enough water to make 500 milliliters of solution? So we're given enough information to calculate moles, and we're given volume. We simply have to get the slope of the line. So moles of sodium chloride go there, liters of solution go here. We're not given moles of sodium chloride, we're given grams. Step one, we get to moles. We're given a volume of a solution, so let's say half a liter. All we're doing is dividing y by x to get the slope. Right? So step one, get to moles. This is the y variable. To now get the slope, we simply divide the moles of sodium chloride by the volume of solution. And we could write it either 0.512 moles per liter, or just leave it as capital M. It means the same thing. And notice 3 sig figs here, 3 there, 3 there, 3 there, and 3 there. Try some of the practice problems and review questions using this approach to see how it works for you. Meaning, you might find it useful, you might not. I don't ever require a graph unless I ask you to draw a graph or a bunch of wheels for you to answer a question carefully. It could be any analogy you want, as long as the calculation I see is correct. Now, there's one final topic in here, and that's ions in solution. But up to now, you guys should be able to do the practice problems on the top of page 150 and the practice problems in the middle of page 151. That's all I'll ask you to look at for Tuesday. what I wanna do, at least for a few minutes, is now use the graphical approach we just took to talk about dilution chemistry. One of the labs you guys are gonna be doing in chapter 4 involves a number of stations where different types of reactions will be occurring. And 2 of those stations are gonna have 2 molar hydrochloric acid, which is plenty strong enough to damage your eyes and your skin. But it's much less concentrated than how I buy hydrochloric acid. I buy it as 12 molar. I buy nitric acid at 15.6 molar. Sulfuric is 18 molar, far too concentrated to be safely used in a high school lab, so I got it diluted. When I'm diluting anything, if I've got a concentrated solution and I wanted to dilute it, do I add more solute or do I add more solvent? What do I add?
Solute.
Solute or solvent? Solute's the thing I dissolve in the solvent. If I add more of that, is that going to dilute the solution? No. I add more solvent, don't I? So let's consider that as we draw the graphs representing diluted system. If molarity, if concentration is the slope of the line, then obviously the steeper the line, the higher the concentration, right? So let's, actually I don't need this for the next few minutes. And this is not actually something you guys need to draw or write down. Because what I'm writing on the board now, I wrote exactly in chapter 7. Okay? I just want it to make sense. So here's our generic molarity graph. Moles of solute, doesn't matter what it is, goes on the y-axis. Liters of solution or volume of solution goes here. So let's say we start off with a concentrated solution. And I'll represent the concentrated by a real steep line, all right? So that concentration I'm going to call M1, the concentration of the concentrated solution before the dilution. And let's say that I have a certain volume of that concentrated solution. I'm going to call that V1. Now, how many moles of solute are in that volume of that concentrated solution? Well, the y variable is moles, right? And you guys know that y equals mx. So what is m? M is molarity. So moles per liter, that's m, times liters, that's x. Always have to give moles of solute. All right? So, the moles of solute in this concentrated solution is just, let's use the ruler, that volume times that concentration, right? M1, V1, right? Now you told me when I dilute it, I don't add solute, I add solvent. So that doesn't change, does it? But if I add solvent, the volume goes up. Let's say the volume went from V1 to V2. This hasn't changed, has it? So the moles before the dilution has to equal the moles after the dilution, doesn't it? Because all I added was salt, in this case water. So the volume's gone up. But because the moles hasn't changed, the concentration has come down, right? So here's the new slope of the line. The y variable didn't change, but the x and the m certainly did, because the volume went up, molarity went down. So let's call this new volume V2, that's the volume of the diluted solution. And let's call the new molarity M2. So the moles of solute before the dilution was M1 times V1, right? Moles per liter times liter. After the dilution, it didn't change, did it? So that's moles before, that's moles after. In virtually all of the dilution calculations you guys will see, not just this year, but next year. Write that down, and it'll allow you to do the calculations. Just like whenever you see the letters STP somewhere, you write 22.4 liters per mole. If you read a question and you perceive it to be a dilution thing, write that down. Now, where have I put that in the book? Well, I'm so glad you asked. Let's go to chapter 7. That's not chapter 7, that's chapter 6. That's chapter 6. That's chapter 7, but not quite yet. There. So give me the page reference and just a sec here. Excuse me. Page 380. And you'll see why you didn't really have to write it down. The reason I added it to chapter 7 is because chapter 7 is a solution chapter, but MEG doesn't ever generate M1 V1 equals M2 V2. I don't know why. When we prepare a dilute solution from a more concentrated one, this is how we started a couple minutes ago, we do so by adding solvent and not solute. This means that after dilution, the moles of solute present in solution are the same as before the dilution. So, moles before, moles after. Moles of solute equals molarity, M, times volume, X. Let's let M1 and V1 represent the initial molarity and volume of a solution before it's diluted, and M2, V2 representing the final molarity and volume of a solution after it's diluted. We can therefore represent the moles of solute present before and after using M1, V1 and M2 and V2, and they have to equal each other. And two things multiplied together giving the same value means that in any given solution, molarity times volume is inversely related. As the volume goes up, molarity goes down. As the volume goes down, molarity goes up, but they gotta multiply to get the same thing. Moles, because moles haven't changed, okay? In virtually every dilution calculation that you'll see, you will be given information about 3 of the above 4 variables, and simply need to calculate the 4th. Very often, you don't even care how many moles of the solute actually exist. All we care about is that it doesn't change. When solving dilution questions, identify which of the above 3 variables you're given, which unknown variable you're asked to solve for. Then simply manipulate the above equation by isolating the unknown variable, put in the numbers and do the arithmetic. Giving you a few examples here as well. What concentration results when enough water is added to 1.5 liters of a 4 molar sodium hydroxide solution to give a final volume of 6 liters? Well, you read the question, clearly it's a dilution question, so you write M1 V1 equals M2 V2. Then read it again to find out which of these things you know and which one you don't. Well, 1.5 liters of a 4 molar solution, we know our initial volume and initial concentration. We're going to dilute it to 6 liters, so we know V2. That's the new concentration. So before you do any calculations, manipulate the equation. M2 equals M1 V1 over V2. By whatever amount the volume went up, the molarity went down. So if I start at 1.5 liters and I end with 6, the volume's been multiplied by 4 times, which means the concentration has to go down by 4 times. So there's M1, 4 molar. There's V1, there's V2, because that divided by that is a quarter. The final volume is a quarter of what you started with. I like to manipulate it before I put the numbers in. That way you see the units have to be correct. Units of volume cancel, you'll end up with molarity. All right? So that's solving for M2. But there's also V1, there's also V2, there's also M1. Example 2. What volume of water must be added to 1.5 liters of a 5 molar sodium chloride solution to result in a final volume of 2.5 molar? Well, it's a dilution question. Write M1 V1 equals M2 V2. What do we know? Well, we know V1, we know M1, and we know M2. What we don't know is V2. So when we wrote this, read the question a second time, I know that, I know that, I know that, I don't know that. So write the equation like this. The initial molarity is 5 molar, the initial volume is 1.5, the final molarity is 2.5. If the molarity went down, the volume has to go up. So if the molarity has been divided in half, the volume must have been doubled. So 3 liters. But the question doesn't ask what's the final volume. We're given the final volume. We're given the final molarity, but it doesn't ask that. It asks how much water would we have had to add to it. If we started with 1.5 liters, we've got to add 1.5 to get 3. All right? There's another one. This one's comes under the heading of diluting acids. This is, I picked 2 molar here as my final concentration, because that's exactly what I have to do when I take the concentrated hydrochloric acid in the chemical storeroom in the acid cabinet and dilute it to 2 molars for the lab we do in chapter 4. What volume of 12 molar hydrochloric acid, which is how I buy it, is required to produce 4 liters of a 2 molar HCl solution? So let's say I need 4 liters for all 3 classes, and it has to be 2 molar, but all I have is a jar of 12 molar. Well, it's a dilution, so again, write this. Now we read the question a second time. What do I know? I know my initial concentration. I know my final volume, and I know my final concentration. What I don't know is V1. So when I manipulate that equation to solve for V1, I get this. Now notice that M2 is less than M1, which means V1 has to be much less than V2. So on the graph, I know M1, I know M2, I know V2. What I have to calculate is V1. I expect a small volume, right? So put the numbers and the units in, I get 0.67 liters. So 670 milliliters of the acid is what I'm going to need to make that volume of the dilute solution. But what if the question, instead of asking for what volume of acid do I need, what if it asked for the recipe? Describe how you would prepare. that should be a little L, not a capital L. Yeah, it's a capital L in your book, it's in this one, it should be little. Now, if we were just diluting a salt solution, let's say we wanted to turn a 12 molar salt solution into 4 liters of a 2 molar salt solution. Not a problem. Start off with a concentrated solution, just add water. But the recipe for an acid can't do that. Because remember, you never add water to a concentrated acid. That's the volume of acid you need, sure. But you can't say, put that in a graduated container and add water to it. Because if you do, as soon as the water hits the acid, it's going to turn into steam. So you're going to generate steam bubbles, gas bubbles inside the concentrated acid, which means you'll end up wearing it. And you don't want to wear a 12 molar HCl. You can't even open that bottle unless you're under a fume hood, because hydrogen chloride gas comes off. And it goes up your nose and turns back into hydrochloric acid, which hurts. So you can't just add water to it. So let's go through the calculation. V1's the same, 0.67 liters. The actual calculation is identical to example 3 above, but you must also include the recipe. The difference here is that rather than starting with a pure solute, like the calcium chloride, which we added water to, you're converting one solution into another. Often the recipe for an aqueous dilution will simply direct that a given volume of water be added to a given or calculated volume of a concentrated solution to give the final dilute solution. In this case, though, we must remember that we never add water to concentrated acid. So we know how much acid we need. We know what our final volume and concentration is going to be. We just need to know how to put it together. There's various ways to remember the rule. Some call it a name W rule, acid into water. But WAW is a little more specific. It means you start with a whole bunch of water, carefully add the acid, and then finish to a final volume by adding water. So you start with water, you end with water. So we begin with a relatively large volume of water, add the required concentrated acid volume slowly and carefully. Usually you add it down a stirring rod to that big volume of water. So for example, we know we want our final volume to be 4 liters. So let's say we started with 3 liters of water. You add a little bit of acid to a lot of water slowly. Now if you add 670 milliliters of acid to 3 liters of water, you're not going to get 4 liters. The solution's still going to get hot. The beaker's going to still get very hot, but you're not generating any steam bubbles. Once you've done that, then you finish, complete the dilution by then adding enough water to achieve a final volume of 4 liters. And you might think, well, why don't you get precisely the amount of water you need, so when you put 0.67 liters of this in it, you're going to get 4 liters. Acids don't mix that precisely with water. So the molecules actually get in between each other. So if you add 670 milliliters of concentrated hydrochloric acid to 330 milliliters of water, you're not necessarily going to get 4 liters of solution. So add a little acid to a lot of water, and then finish by adding water. Okay? Now, because this technically is a Chapter 7 topic, dilution chemistry, if I ask anything about dilutions on the Chapter 3 test, it'd be a bonus question. All right? It's not like we're short of questions to ask in the Chapter 3 test. But if I do ask a dilution, there'll be extra marks attached to it if you want to do it. Which means technically you can get more than 100%, but if you choose not to do it, it's not going to cost you. If it's there, and you do any of it and get any of it right, those are free marks. depending on your time. We're not finished chapter 3 yet, but because there are 6 sections and because I can't ask you everything we did in one period, probably Thursday of next week. We meet Tuesday, which is a full block. Thursday's like, I don't know what, half an hour maybe, give or take, because of Mass. Probably on Thursday, I'll give you a little more detailed idea as to what you should focus on for the test. In other words, I already gave you the first 2 questions. The last page of the worksheet, that type of question, and a formula determination. Obviously, there's going to be others. There's going to be some solution stuff. But anything like this would be the last question, and it would be bonus. Okay? The test is not going to be immediately upon your return. I can finish chapter 3 quite easily on Tuesday. But we also have to allow, ideally anyway, a full class for a review, which means that can't be Thursday. When we get back after Christmas break, that week is Chancellor Week. So I think beginning on Wednesday, we have our games. I'm not betting that we're gonna have too many full classes on the first week back. So the test won't be the first week back after Christmas vacation. We still have to have a review class. The soonest it would probably be maybe the middle of the next week. So you don't have to ruin your Christmas vacation by studying camp. Not that that would ruin your Christmas vacation, but you might have other stuff to do. But knowing what it is you should focus on is something I will give you before you leave for Christmas break. Okay? We're going pretty quickly here, but notice we are just finishing chapter 3. There's 8 chapters in the book. We have 5 more to do, and we're at Christmas already. So, this is pretty much always the case. But if it seems like I'm going pretty quickly, I'm kind of have to continue to go pretty quickly. But I'm relying on you. If whatever I'm talking about doesn't make sense, or when I ask you to look at stuff for homework and check your answers, if when you do that you're not getting the right answers, then stop me, and we'll go through the problems that you have. And that's the purpose of homework. But we do have 5 more chapters to do after chapter 3. You might be happy to know that chapter 3 is the last one here. Chapter 4, Sherry wrote that. She does a really good job. We don't have to do all of it. One of the sections we don't have to do. 5 and 6 we will get through, but after 6 we go to 8, and time permitting we come back and do some of chapter 7. And another reason I wanted to talk about dilution today is in years past, we haven't had time to do much of chapter 7. But at least some dilution chemistry we have touched on. Meg wrote 7 and 8, I wrote 5 and 6. Sherry wrote 1 and 4, Gary wrote 2 and 3. You're gonna see chapter 4 is written quite well, and that's a hallmark of Sherry's stuff. But that's not gonna happen until after Christmas. And really, everything we've done up till chapter 4 prepares you for chapter 4. So that's where all the mole conversions, all the stuff get woven into what we call stoichiometry, where we calculate with chemical amounts, right? But that's still coming. So, you've got, I don't know, 5 minutes. All I've asked you to do for Tuesday is have